In the next subsection, I want to motivate why we study this problem. And maybe that also triggers some thoughts for you how efficient we want to solve RMQ instances. So here this is obviously the new abbreviation range-bin queries. You might remember what these are. I won't mention the last. These are the longest common prefixes. That is Unit 6 calling. And you might also remember the longest common extension problem, also Unit 6, and the lowest common ancestor in trees. That's something that we also mentioned in Unit 6, but only in passing. So let's recap a little bit, and I just copied the slides from back then. So if you're a graphically oriented person like myself, you profit from seeing the exact same thing, the same arrangement. So here it is. We talked about the longest common extension problem. You're given a string. My favorite diagram for this was like this. So you have two positions in a string, I and j, and you ask what is the longest piece of text that you can read so that it's the same text if you start at I and at j. So these two things should be the same. And of course, because it's longest, it means if you go to the next position then is not the same. Otherwise, your longest common extension would be one bigger. Well, formally, the longest common extension was the length of this green part, not the string, just another nitpick to make it a little more convenient. And we've already at the time found this connection. There's an obvious connection between LCE and the suffix tree. The longest common extension of two positions is the longest common prefix of two suffixes, namely those starting at those positions. And in the suffix tree, we can find longest common extensions by taking the lowest common ancestor of the leaves for those suffixes and then computing its string depth. So our example back then was this banana ban. And so you could, for example, ask what's the longest common extension starting here and here. That's position 0, 1, 2, 3, 4, 5. So if you execute this, you would find I and j here and here. Their lowest common ancestor is this node, and it has string depth 1. So that would mean I can read one character that is equal, and then the next one is actually already a mismatch. And that works out in our example. Okay. That was what we noticed at the time. And then we found that this longest common extension problem is really useful in doing all sorts of extra clever algorithms on strings using the suffix tree plus this LCE data structure allowed us to solve some other interesting problems. Remember the kangaroo algorithm for finding approximate matches. And at the time I left this, so this is the main point here of this slide. At that point, I told you there is a magic black box for the LCA problem, finding lowest common ancestors in constant time with linear time pre-processing on the tree. And that can solve LCA and hence also LCE in an arbitrary string by using the suffix tree. Okay. So that is a reminder of what LCA and LCE was. The next thing to remember is we also had LCP, the longest common prefix. And that was when we talked about suffix arrays. Not suffix trees, but arrays, suffix arrays. Instead of looking at this LCA question, we can now look at arrays. And so this is nothing we wrote down at the time, but let me illustrate that on an example before we move on. So again, slides from back then. Remember, just for getting the notation in everyone's head again, we had the suffix array L, the leaf array, had the leaves of the suffix tree in sorted order. That is just the suffixes in sorted order. L tells you where does this suffix start, the first, the second, etc. in the sorted order. And we also had R, the rank array, which is the other direction you have for the inverse permutation. You have the starting positions in the text, and then R tells you what is the rank in the sorted list. And so you can use this to go right and left in this picture. Now, what I'm saying here is, suppose we want to find the longest common extension in banana ban. Again, okay, let me write this again. So let's pick the same example. I take this position here, this A and this A, and I want to find from the suffix array, from this suffix tree, I want to find what's the longest common extension. So how much to the left can I walk from this position and get the same string in both cases? We already know it's just the A, but suppose we didn't know. First of all, we find this is position 1 and 5 in the string. So we find positions 1 and 5 in the string here. That's the leaves, banana ban and A ban. Now, the going to the right, I should have probably started here. We know it's position 1 and 5. We can use the rank array to tell us where in the sorted list we find this, namely position 4 and 1. 4 and 1. So here we have A ban and banana ban. Position 1 and 4 in the sorted list. That was the rank. Right, this is just, oops, no, this, okay, now, we had this before. My tool crashed again. Let me open it and hope that it can restore the drawing from now. Not clear what it didn't like now, but there we are again. Okay, it's only a couple of things that didn't get stored for whatever reason. Okay, one more time. Where are we? I'm trying to find the longest common extension of anaban and aban, or the longest common extension of these positions 1 and 5 in this string, really. I use the rank array to find where in the sorted list I find these two suffixes. Then when I found them here, I can use the LCP array entries here. Those are the lengths of these overlaps between adjacent suffixes in sorted order. Okay. And now the cool thing is I take this range and find the range minimum query in that range, the smallest value in that range, which is 1. And 1 is also the answer. We have 1 character overlap between these two things. So this is the connection that's spelled out here in big. If I want to find the longest common extension between two positions I and j, I take R, the rank array, to map them into this picture on the right, where I have them in the sorted order. They might flip positions, so 5 becomes 1 and 1 becomes 4. So even though I was less than j, now R of I is bigger than R of j. That's why we use min and max to get those two right. And now I take this as a range here in the LCP array and find the minimum in that range. And because it's a subarray, I can use the range minimum query in the LCP array for that. And here you see I access the LCP array at that index. RMQ returns the index. LCP is the original array. So I find just the smallest value in that green range, and that is my result. Okay. And the reason for that is simply that if this string and this string have anything in common, then all of the strings in between have anything in common, have the same thing in common. And we also have to have one place where this value occurs, where this minimal shared prefix exists. If all of the values in between were bigger, then also the top and this is A ban and N ban would share more than one character. So I know this this slide was dense and full of somewhat complicated relationships. So let's zoom out even graphically a bit more. The reason here why I repeat this in detail is just to motivate why the range minimum query problem occurs here. It is effectively another way to solve this longest common extension problem, but in the array world, not on trees. This doesn't need the suffix tree anymore. The only thing we need is the inverse suffix array and the LCP array. And we've seen in Unit 6 already how to compute both in linear time with reasonable algorithms that you could implement in, well, say a few days or weeks of concentrated effort. But it's not crazy, not too crazy, and there are implementations available in libraries that one can use. So what does it mean to have RMQ for LCE? We can compute, it's basically what I said, we can compute the inverse suffix array and the LCP array in linear time. So whenever I have a PQ solution for range min queries, that means I have a PQ, same P and Q solution for longest common extensions.